In this lesson, we're going to explore one of the most important discoveries in electronics history, how Bardeen, Brattain, and Shockley developed the transistor by carefully analyzing current voltage curves and building mathematical models to explain the behavior they observed. John Bardeen, Walter Brattain, and William Shockley worked at Bell Labs in the late 1940s. They were trying to understand strange electrical behavior in semiconductor materials, specifically germanium. What they discovered changed the world forever. Bardeen was the theorist who understood quantum mechanics. Brattain was the brilliant experimentalist who could measure tiny currents. Shockley was the director who pushed for practical applications. Together, they formed a perfect team. In 1947, they were studying the surface of germanium crystals. When they applied voltage, the current didn't behave like a simple resistor. Something strange was happening at the surface. Let's understand their initial approach. When you have an unknown electrical component, the first thing you try is Ohm's law. Does it behave like a resistor? Ohm's law states that voltage equals current times resistance. For a resistor, if you plot voltage versus current, you get a straight line. Here's what a resistor looks like. The current versus voltage plot is perfectly linear. The slope gives you 1 over the resistance. Simple and predictable. However, when Brattain measured the current through their germanium setup, he got curves that looked nothing like straight lines. Look at this curve. At low voltages, almost no current flows. Then suddenly at higher voltages, the current shoots up exponentially. This is definitely not a resistor. Let me ask you a question. Why couldn't they just pick a single resistance value to describe this device? The answer is that the effective resistance is changing dramatically with voltage. At low voltage, the resistance is huge, maybe millions of ohms. At high voltage, it drops to just hundreds of ohms. The effective resistance, which is voltage divided by current, is not constant. It depends on the voltage it's. This violates the fundamental assumption of Ohm's law. Here's where the breakthrough came. Bardeen and Brattain realized that the current didn't just depend on the voltage between two terminals. There was a third terminal, and the voltage or current at that terminal controlled the main current flow. Imagine a device with 3 terminals: collector, emitter, and base. The current flows from collector to emitter, but the amount of current is controlled by what happens at the base. This is the transistor concept. To understand this behavior, they created what we call characteristic curves. These are multiple current voltage plots, each one corresponding to a different base current. Here are the characteristic curves for a bipolar junction transistor. Each horizontal line represents a different base current. When base current increases, the collector current increases proportionally. This is amplification. Now let's talk about the mathematical model they developed. For the junction between the base and emitter, they found an exponential relationship. The current equals I0 times the quantity e to the v over nVt minus 1. Here I0 is the saturation current, V is the applied voltage, N is the ideality factor, and Vt is the thermal voltage. The thermal voltage Vt equals kT over Q, where K is Boltzmann's constant, T is temperature in Kelvin, and Q is the electron charge. At room temperature, this is about 26 millivolts. You might ask, why exponential? This comes from quantum mechanics. Electrons have to overcome an energy barrier at the junction, and the probability of crossing depends exponentially on the voltage. Think of it like rolling a ball over a hill. If you increase the energy of the ball, exponentially more balls make it over. Small increases in energy can cause huge increases in the number of successful crossings. To fit their model to the measured data, Bardeen and Brattain had to adjust several parameters. Let's see how this works. First, the saturation current I0. This determines the overall scale of the current. It depends on the material properties and the geometry of the device. Second, the ideality factor N. For an ideal diode, N equals 1. But real devices have recombination and other non-ideal effects, so N might be between 1 and 2. Third, the current gain beta. This tells you how much the collector current increases for each unit increase in base current. For a good transistor, beta might be 100 or more. The collector current equals beta times the base current. This is the fundamental amplification equation for a bipolar transistor. Let's work through a concrete example. Suppose we measured the following data points from an early transistor. Here's our data. Notice how the current increases by a factor of 10,000 as voltage goes from 0.2 to 0.7 volts. This huge dynamic range suggests exponential behavior. To test for exponential behavior, we take the logarithm of the current. If the relationship is exponential, log I versus V should be a straight line. And look at that. When we plot log current versus voltage, we get a beautiful straight line. This confirms the exponential model is correct. The slope of this line is 1 over n versus t. From our data, we can calculate the slope and then solve for the ideality factor n. If the slope is about 15 per volt and Vt is 26 millivolts, we get n approximately equals 1.5. This tells us the device has some non-ideal recombination. For a bipolar junction transistor, there are 3 distinct regions of operation that Shockley identified mathematically. In cutoff, both the base emitter and base collector junctions are reverse biased. Almost no current flows. The transistor is off. In active mode, the base emitter junction is forward biased and the base collector is reverse biased. This is the normal amplification region. Current gain is maximum here. In saturation, both junctions are forward biased. The transistor is fully on. The collector current is limited by external resistors, not by the base current. Here are the 3 regions on the characteristic curve. Understanding these regions was crucial for designing circuits that could reliably amplify signals. Now let's talk about field effect transistors, or FETs. These work on a different principle than BJTs, and they need a different mathematical model. The key difference is that FETs are voltage-controlled devices. The gate voltage controls the drain current, not the gate current. In fact, ideally, no current flows into the gate. A FET has a gate that controls current flow between drain and source. The crucial point is that no current flows into the gate. The gate voltage creates an electric field that modulates the conductivity of a channel. In the saturation region of a MOSFET, the drain current follows a square law relationship with gate voltage. Drain current equals 1/2 mu Cox times W over L times the quantity VGS minus V threshold squared. Here mu is carrier mobility, Cox is oxide capacitance, W and L are channel width and length, and V threshold is the threshold voltage. The square law comes from the physics of how charge accumulates in the channel and how the electric field shapes the conducting region. It's fundamentally different from the exponential law of BJTs. Students often ask, which is better, a BJT or a FET? The answer is, neither is universally better. BJTs have higher transconductance and are better for analog amplification. FETs have higher input impedance and are better for digital switching and low-power applications. The transistor models that Bardeen, Brattain, and Shockley developed didn't just explain puzzling measurements. They enabled the entire semiconductor industry. In December 1947, they demonstrated the first working point contact transistor. It amplified signals, but it was fragile and irreproducible. In 1949, Shockley developed a complete theory of the bipolar junction transistor with the equations we've been discussing. This made transistors manufacturable. In 1956, all 3 shared the Nobel Prize in Physics for their work on semiconductors and the discovery of the transistor effect. Today, engineers use sophisticated parameter extraction techniques to fit transistor models to measure data. First, measure current voltage curves at multiple temperatures. This helps separate temperature-dependent and temperature-independent parameters. Second, use nonlinear least squares fitting algorithms to minimize the error between the model and measurements across all operating points. Third, validate the extracted parameters by building test circuits and comparing measured performance with simulations using your model. Here's what a good fit looks like. The red dots are measurements. The green curve is the model. When the model accurately captures the device physics, the fit is excellent across the entire operating range. Modern circuit simulators like SPICE use incredibly detailed transistor models with hundreds of parameters. The BSIM model for MOSFETs has over 100 parameters. These capture short channel effects, velocity saturation, hot carrier effects, and many other physical phenomena. For BJTs, the Gummel-Poon model extends the basic Ebers-Moll equations with additional effects like base width modulation and high injection behavior. Yet, at the core, all these models are built on the fundamental physics that Bardeen, Brattain, and Shockley discovered. The exponential junction law for BJTs and the charge control model for FETs remain the foundation. Let's conclude with a practical example. How would you use these IV curves to design a common-emitter amplifier? Your goal is to amplify a small AC signal. You need to bias the transistor at a DC operating point in the active region. Then the AC signal causes small variations around that point. You choose a Q point, the quiescent operating point, in the middle of the load line. The AC signal causes small variations in voltage and current around this point. The slope at the Q point determines your AC gain. The voltage gain equals negative Gm times Rc, where Gm is the transconductance and Rc is the collector resistor. The transconductance is the derivative of collector current with respect to base emitter voltage. For a BJT in active mode, Gm equals the derivative of collector current with respect to base emitter voltage, which simplifies to IC over versus T. This comes directly from the exponential model. Let me summarize what we've learned about fitting transistor characteristics. The early transistor-like devices showed puzzling nonlinear behavior that couldn't be explained by simple resistor models. Bardeen, Brattain, and Shockley built models based on quantum mechanics and semiconductor physics. These models had a small number of parameters that could be extracted from measurements. The key relationships are the exponential law for bipolar junction transistors and the square law for field effect transistors in saturation. By carefully fitting parameters to match measured curves, engineers can predict device behavior under new conditions and optimize circuit designs. This model-based approach transformed unreliable surface effects into reliable, manufacturable devices that revolutionized electronics and created the information age. Today's semiconductor industry, with billions of transistors on a single chip, stands on the foundation that Bardeen, Brattain, and Shockley built by carefully analyzing current voltage curves and developing mathematical models that explained and predicted device behavior.